Good morning, everyone. In the previous class, we were discussing about the charge leakage problem, which was associated with the dynamic logic circuits. Yesterday, I discussed a little bit about what is the charge sharing problem, but let us discuss in detail what is this charge sharing problem and how this can happen. Okay, so if you see, like suppose I have a circuit something like this, where we have a pre-charge transistor MP and we have a evaluation transistor AV, and we have a two transistors which are connected in the series, and they are acting as a they will give some particular logic, right? So in that case, if the circuit is in the pre-charge mode, so what I need to do, I need to keep this clock at the high logic 0. And if it is at logic 0, and what one more important thing, because all the internal node must have some capacitance itself, because we have already studied in the RC model that each node can offer some capacitance or the node capacitances. So let us try to draw those load capacitances first, and then we can discuss later on. Okay, so let us assume I have some load capacitance at this node, and let us assume it is CM2. Similarly, we can have some load capacitance at this node as well. So let us consider this load capacitance is CM1. Okay, now what I'm assuming that while pre-charging this dynamic node N, all the internal capacitances like CM1, CM2 are discharged, and both the inputs are connected at the low logic. Okay, so A and B are at the logic low, and all the internal capacitance, whatever we have, all the capacitances are in the discharge condition. Okay, now if I'm connecting this clock to the logic 0, in that case, what will happen? This transistor or this dynamic node will be charged through the pre-charge transistor, and that will reach up to the VDD. Okay, so because both the transistors M1 and M2 are in the off state, so we are not getting any direct path to discharge this one. Okay, but what happens if after pre-charging phase, let us assume I have changed something. I have if the B is still 0, but if I have made some change in the logic at input A, so if the input has changed from logic 0 to logic 1, then what will happen? Because this transistor M1 is in the on state, like this will be in the on state. So what will happen? This load capacitance will start, it will get some path, and it will start redistributed over CL and CA. So whatever the charge is stored at CL will be now redistributed over the load capacitance CL and the internal capacitance CM1. Okay, so this is the one of the important thing, which is really very important. So even though I'm assuming in the pre-charge mode, like if it is in the pre-charge mode, there is no evaluation mode, and if there is some transition in input, one of the input, then the load whatever the charge is stored at the load, that will be redistributed. And if it is redistributed, this will so definitely it will get some path, because transistor M1 is in on state. So some of the charge will be redistributed to the CM1. So effectively the charge at output voltage will be reduced. Okay, so this is the really serious problem, because even in the pre-charge mode, the circuit is in the pre-charge mode, but the charge will be redistributed. Okay, so this is one of the problem which we are calling. So let us try to mathematically derive these particular things. Okay, so to derive these particular things, let us assume initially, we know that simply the maximum voltage at let us apply the charge conservation. So what will be the output? Let us try to validate those things, because the circuit is in the pre-charge mode. So I'm assuming at output the maximum voltage which I will get, like let us assume the supply voltage is VDD. So the maximum voltage will be VDD during the pre-charge mode. Okay. So if I apply the charge conservation, in that case, what I will get? I will get CL into VDD. This was the initial state, and that can be converted like at t is equal to 0, the output voltage was VDD, but after some time, like when I have switched on this transistor M1, or I have turned on this transistor M1, in that case, some of the charge will be redistributed to some of the CM1, and that will be some different time. So let us try to write it like CL, whatever the capacitance left at the load capacitance, and that is nothing but this is the V output at certain time t. Okay, and plus whatever the capacitance we have, like CM1 into let us assume whatever the voltage here, let us assume it is X, node X voltage. So this will be like Vx. So this is what we can apply the charge conservation on how it is distributing. Okay, so if we try to calculate, like because the transistor M1 is in on state and we have logic high here, so because we know that the MOS transistor cannot pass complete high, there will be some threshold voltage drop. So this Vx can be like VDD minus VTH. Okay, so this Vx can be like Vx is equal to VDD minus VTH. Okay, so if I try to apply all those things, Vx is equal to VDD minus VTH. So how the equation will look like, let us try to see here. Yeah, we just need to put in the above equation, and then we will get the change in the output voltage. So initially output voltage was VDD, and later on it becomes the V out T, particular something like that. Okay, so if we try to calculate delta V output or change in the output voltage after certain time period T, so that we can calculate like initially it was VDD minus V out T simply. Okay. So this will be the change, and if we try to calculate from the above equation, simply it will be like CM1 divided, you can calculate it, it's very simple, like so CL into VDD minus VTH. Okay, so this is what the delta V out T is. So the important thing is, what is the importance of this equation, this derivation? The importance of this equation is like, if the change in the output voltage, what was the initial voltage and what will be the output voltage after a certain period of time, that depends on the load capacitance ratio and the whatever the internal capacitance is there. Okay, so this depends on the internal capacitance and the load capacitance ratio. So this is really one of the important thing which we should consider.
Hello, sir.
Yes.
Sir, can you explain that first equation again?
Yeah, this is simply the charge conservation. Initially, if you see here, initially I am assuming that the because the circuit is in the pre-charge mode. Okay, here we have this clock is equal to 0. The circuit is in the pre-charge mode. So whatever the supply voltage we have, this dynamic node will be charged. So the output voltage is nothing but it will be same as the VDD. Okay, so this load capacitance will be charged up to the VDD. So if we apply the charge conservation, so this is what initially we have the voltage at the output, which is the VDD. Now after certain, because what I have done, because the transistor M2 is in the off state, and we have changed the state of the input of this transistor M1 from 0 to 1. So transistor M1 is in the on state. So there some of the charge will be redistributed to the CM1. Okay, if some of the charge will be redistributed, so what we can see, after a certain period of time, the output voltage will be like V out T. I'm just writing V out T because at time t, we have some output voltage which is somewhat less than this VDD. This, yeah, of course, this is very important. Like the V out T is less than VDD. It is not is equal to VDD. Because it is this T is not equal to 0. Okay, so if I have activated transistor M1, in that case, V out T will be less than VDD. So this is one of the condition. So here it will be like if we apply the charge conservation, CL into V out T plus some of the charge is redistributed to the CM1. So it will be like CM1 into the voltage, whatever here at X. Okay, so it will be CM1 into Vx. And because this M1 is the NMOS transistor, and NMOS transistor cannot pass the maximum logic, there will be some threshold voltage drop. So initially the voltage was VDD, but it can pass up to VDD minus VTH. So the Vx can be like VDD minus VTH. Okay, so if we put this Vx into the equation number 1, then the difference will be nothing but like the change in the output voltage will be the whatever the original value we have. This VDD is nothing but this is the V out at T is equal to 0. Okay, so this VDD, this is nothing but this is V out at T is equal to 0, and this is VDD minus V out at certain time. And then if we differentiate these two things, and we will get some equation, something like this. And we can say like now you got the answer?
Yes, sir. And sir, that is why to bring VDD again back to to bring Vx, we get Vx as to bring Vx back to VDD, we are using the keeper transistor at point X.
Yeah, so we will use it. Yeah, I will explain it later on. So no problem. Just wait, and I will explain your. I think your doubt, all the doubts I will clear. I will try to answer all the questions. No problem. So this is what the difference. The change in the output voltage is, and this is really very important. So this is the case if I'm providing like the if the delta V out is less than VTH. Okay, so this is the case. Like if the delta V out is less than VTH, then the this will be the condition, and this is how this circuit will work. If we talk about like suppose if the delta V out is greater than threshold voltage. Okay, so if the change in the threshold voltage or change in the output voltage is greater than threshold voltage, in that case I'm assuming that the V output, whatever the load capacitance will charge, that will equally redistribute to the CM1. Okay, so in that case what will happen, the delta V out, because the CL will equally redistribute to CM1, so the resultant delta V out at T will become VDD. Yeah, because it is decreasing. So because the charge initially, whatever the charge was, that is decreasing. So we can keep minus sign here also and here also, like the whatever the VDD was there, and that this is simply divider formula will be applied. So CM1 divided by CL plus CM1. Okay, so this is the actual equation if the VDD is greater than VTS. So this is for delta V out is greater than VTH, and this is for delta V out is less than VTH. So these are the two conditions, and this is really very important. So the important thing is like what we are desiring. If we see the second case, in the second case, like the change in output voltage will be exactly half if and if the both the capacitance are same, something like that. So it will depend on whatever the capacitance is there, and that will be redistributed. So I'm assuming that like if the load capacitance is discharging or it is redistributing to other internal capacitances, might be the output voltage will not be the same, and might be it can be below the threshold voltage or above the threshold voltage. So that will create the problem, like whatever the logic we will connect next to this circuit, that may malfunction. So this is one of the problem. Yeah, let me repeat it again first, then I think your doubt will be clear. then you can ask. Okay, so what I'm saying, suppose whatever the maximum voltage we have stored at the CL, okay, in that case, suppose if the output voltage is redistributed, which is very close to the threshold voltage of the circuit, or the switching voltage, so might be that voltage will be very less, and that may create the malfunction. So this is one of the problem. Yes, please ask the question, then I will answer.
Sir, why is there minus sign in delta V out?
And because initially what was the voltage we have, that is decreasing, so that is why I'm keeping minus sign. So you can take the modulus to understand it. Okay, so because the voltage is decreasing, so that is why I kept it negative.
Sir, how did we get the second equation?
Second equation is simply because see here, if the change in output voltage is strong enough, like which is greater than the threshold voltage of the transistor, in that case what will happen, it will act as a simply the divider one, like the capacitance will equally divided, like it will be divided between the CL and the CM1. So we just need to, whatever the maximum voltage we have, and we need to apply the voltage divider formula. So the CM1, because the charge is redistributing to the CM1, so CM1 divided by the total capacitance CL plus CM1. So this is how it is coming. Okay, and yeah, this completely depends on what is the internal capacitance we have. So both the states, whatever we explained here, this depends on like how many change are there, like what is the change in the output voltage. Okay, so hope you got all the answers. Can we move ahead with this?
And sir, this condition delta V out less than VTH, or whether it is greater than VTH, that depends on the capacity of CMOS, right?
Yes. So internal capacitance, this play a major role on the what is the how much charge can be distributed, because if the CM1 is very less, right, so might be there is no leakage problem, like there is no charge sharing problem, and that CM1 depends on the what is the size of these transistors, like the drain and diffusion capacitances. So if somehow we are able to reduce the internal capacitance by reducing the drain and diffusion capacitances, so you can reduce the internal capacitance at certain node X, and that will effectively reduce the internal capacitance, and the charge sharing problem will, okay, we can avoid the charge sharing problem. Yeah, this is really very important. I think I have already told you in some of the layout designing, when I was designing the two layout of NOR gate, two kind of structure, and if there are three paths are coming and four paths are coming, so diffusion capacitance will be different for each layouts. I think you can remember that lecture. So the layout is a really very important, how we are making our layout of any particular circuit, and if we are able to make the perfect layout so that we can reduce the diffusion capacitances, so effectively the internal capacitance can also be reduced. So this is really important. So at the layout level, we can think of to remove this charge sharing problem, but again 100% internal capacitance cannot be overcome, that cannot be removed. So there will be the charge sharing problem always. Okay, so to overcome that problem, what we can do, we can consider a clock driven keeper transistor, as I have already discussed these things in yesterday's lecture. So suppose this is the circuit. So what I will do, I will simply connect a keeper transistor, which will be drive either we see, let us assume I am connecting it with the ground. Okay, so if I'm connecting it to the ground, in that case this will always charge this internal node voltage, which is not correct. Might be we need to turn off both the transistors M1 and M2. So in that case, we cannot use the always on keeper transistor. We can use the clock driven keeper transistor, which is nothing but this is clock. So based on the clock, it will charge and the discharge. So during what it will do, suppose I have a internal capacitance over here, which is the CM1. Okay, so what will happen during the pre-charge phase? Definitely it will pre-charge the node, this dynamic node N, and because this keeper transistor is also in on state, so if it is on state, this will also precharge this CM1. So if the CM1 is precharged, and if let us assume this B is equal to 0, and I'm changing A from 0 to 1. So even though I have changed from 0 to 1, because this internal capacitance is already charged, so this charge, load capacitance charge, will not be redistributed to the CM1. So this is how we can overcome this problem. Because this CM1 is already charged, so the charge redistribution will not be possible further. Okay, so this is how we can achieve, or how we can overcome this charge redistribution problem. Okay, so this is nothing but this is the we need to precharge the internal node using the clock driven transistor. But yeah, the important thing is like because this transistor is on and all the transistors, so might be it can increase the power dissipation, and also somehow the area will also be increased. So this is the problem with this one also. But yes, we cannot overcome all the problems, but that can overcome the charge sharing problem. So now the things are clear from the yesterday's lecture. Any doubt?
Yes, sir. Will there be any power dissipation? I don't think there will be power dissipation.
No, ideally there is like we are not getting any direct path to for the power dissipation. But the thing is, because this clock is during precharge phase, let us assume I have kept this B is equal to 1. Okay, and let us assume I have removed this evaluation transistor, means I am considering the footless kind of dynamic circuit. Okay, so in that case, because this is 1 and I'm assuming I need to precharge this node. But now let us see, during precharge phase the input can be anything. It's not necessary the input will always be in the off state, or the transistor will be in the off state. So if I am using the footless kind of structure, so this is in the on state, and what it will do, because this is in the on state, even though this transistor is off in the off state, it will get some path like this from here to here to make a VDD to ground path, and there will be some direct path, something like that. Yeah, in certain cases definitely there will be power dissipation. You got the answer?
Yes, sir.
Okay, so this is how the power dissipation can be there. Yeah, of course, in this particular circuit, ideally you will not get the power dissipation, but if you are using the footless kind of structure, in that case you will get the power dissipation. Okay, so yeah, so this is how you can explain this problem. Now let us go ahead with the third kind of problem, which we call it the backgate coupling. What is this backgate coupling? Let us try to understand these things. Okay, so suppose currently I have a dynamic NAND gate, 2-input NAND gate, which we have designed based on the dynamic logic circuits, and I have kept A and B both is equal to 0 here. Okay, so if A and B both are in 0, logic 0, so whatever the input we will provide, like if the clock is equal to 0, in that case the node will be precharged, and during evaluation phase again it will be charged only, so it will not be discharged. Okay, now let us consider I have connected some of the static kind of circuit, like static NAND gate, just after the dynamic NAND gate. So this is nothing but one of the input of the static NAND gate is taken from the output 1, and where the output 1 is nothing but this is the output of the dynamic NAND gate, and the second input is here, which we are providing like low to high swing. Okay, so in case if I will provide, ideally what will happen, let us see, because we have precharged this transistor, this node, we have already precharged this node, so this output is nothing but this is at logic 1. Okay, so this output 1 is nothing but this is at logic 1, and if it is at logic 1, what will happen, there will be some charge differences, like there will be some capacitance, diffusion capacitance across this transistor, because if this is 1, this transistor is in the on state, and if it is in on state, it will offer some of the capacitances. Okay, and if it will offer some of the capacitances, So definitely I'm assuming that because this is the one of the input is at logic 1, and the second input I am changing from low to high, and if I'm able to do like this, the output 2 will be is equal to 0, because both the inputs are 1. In that case, output of this static NAND gate will become 0. Okay, so let me explain it again what I'm saying. Yeah, let me continue, then I will explain it again so that you will be able to understand what I'm saying. So because this transistor is always in is in the on state, it will offer some of the capacitances like gate to source capacitance and gate to drain capacitance. So there will be two capacitance that will be offered by this transistor which is in the pull down side. Okay, if it is like this, because during the pre-charge one, or it was in the pre-charge phase, because this output was connected with this one, so this capacitor will also be charged. So what will happen? Suppose I'm changing the clock. I will explain it again, no problem. So let us assume initially the clock was at logic 0, means which was in the pre-charge mode. Now I'm moving into the evaluation phase. Okay, so this in the dynamic and NAND gate, I'm moving into the evaluation phase. Then I'm changing this input after some time. So during the evaluation phase, I'm changing the input from low to high. Okay, then what will happen? Because during this time period, because this output 1 is in the on state, and there are some internal capacitance like the source to gate capacitance and source to drain capacitance. This capacitance will get charged. So effectively, the capacitance, we will have a different capacitance over here. Okay, so this capacitance will be there. There is one capacitance here, and this is one capacitance, this is one capacitance. So effectively, the capacitance will increase, and might be the output during this phase will increase higher than the maximum voltage whatever we have, and we call this particular higher voltage is the feed through voltage. Like this is due to the clock feed through. So this is nothing but this is due to clock feed through. Okay, now if I have provided the input from low to high, in that case this output 1, because this input is 1 and this is also 1, so the output 2 should be 0, but it like output 1 cannot be degraded to the complete 0. So this is what the problem we can get if I have cascaded one dynamic and one static NAND gate or this kind of structure, and if there is some backgate coupling at some of the output, so this kind of problem will come, and we call it the backgate coupling problem. Okay, one more important thing which we need to consider here: how we can isolate, how we can overcome this problem. To overcome this problem, we need to use some impedance matching circuit kind of thing can be done. So, and for that purpose, in between the output of the first stage and the input of second stage, we can use buffer circuit. So buffer circuit is nothing but that can be utilized to for the impedance matching. Okay, and that may overcome this kind of problem which we are observing here, which we are calling like the backgate coupling. Okay, so this is the problem if I have added circuit something like this.
Sir, that can you explain? Like, I'm not getting it.
Okay, so let me repeat it again. Suppose initially, just see the waveform, whatever here we have. Initially, the clock was at logic 0. Okay, during this phase. Okay, so initially clock was at logic 0. Let me use the pointer. During this phase, the clock was at logic 0. And if the clock is logic 0, means the dynamic NAND gate is in the pre-charge mode. So output 1 will be charged to the VDD. Okay, so this is the assumption whatever we have done. So output 1 will be charged to VDD. Because this output 1 is charged to VDD, and I'm not changing this input for some period of time, So what will happen, because this output one is connected to the one of the two transistors, one NMOS transistor and one PMOS transistor here and there, because this transistor will be in the on state due to this one, because it will provide logic 1. So it will offer some source to gate and source to drain capacitances over here, and because of that this capacitance will get charged. Okay, because we have already, and this is in the pre-charge mode, so the charge redistribution is not possible, because this load capacitance will redistribute to these capacitances, these will be charged, but because this is in the pre-charge mode, so again this CL will be charged to the maximum value. So these two transistors, these two capacitors are charged, this is also fully charged. The overall, the output at this voltage will observe due to this capacitance, and this capacitance, because we have not changed the input. Okay, so we will get somewhat higher voltage at the output one due to this one, and we call it the clock feed through. Okay, now once we have changed the input from low to high, so this output will change from high to low. That is perfectly fine. Okay, and this if I have provided something like this, even though this output 2 is low, so if it is low, then it cannot discharge this capacitance completely. So there will be always a capacitive effect due to this one, and the output one will not be 0. So this is the thing which we need to consider, and it is important. Okay, so you got the thing, or still I need to discuss?
Yes, sir.
Okay, so this is what the problem of backgate coupling is. So to overcome that problem, you can use a buffer circuit in between two stages. Okay, so let us move ahead with the other kind of problem. The fourth problem is the clock feed through problem. What is this clock feed through problem? What happens? Suppose I have a dynamic circuit like this. Okay, so if I have a dynamic circuit something like this, and during pre-charge phase I have charged the dynamic node through this pre-charge transistor. Okay, so what will happen, because there is always a coupling capacitance will be there in between clock and the output dynamic node. So some of the coupling capacitance kind of effect will always be there. Okay, so this is nothing but this is in between gate to drain capacitances of the pre-charge devices. So whatever the pre-charge device I have, this is the MP is the pre-charge devices, and for these pre-charge devices there will always be a gate to drain capacitance, which we call like the coupling capacitances. Okay, and these coupling capacitance also include overlap and the channel capacitances. So I think I have not detailed explained about what kind of capacitance we can have in the devices. So later on, I think maybe in the next lecture or next to next lecture, I will explain the different kind of capacitances associated with the transistors. Okay, so that we will be able to understand what kind of capacitances there could be in the transistor. But for simplicity for now, let us consider we have a gate to drain capacitances. Okay, and if there is a gate to drain capacitances, what will happen? Because this CL is always charged, this is charged because of this MP, and because of we have already one more capacitance over here which we call like coupling capacitance, and this will also be charged because of this clock is logic 0, and here it is charged, so charge redistribution will be there, but because this is in the pre-charge phase, so it will again charge the CL. So both the transistors will be fully charged. Okay, and if both the transistors are fully charged, then during a transition there is some spike kind of thing. This kind of the transition we can observe during transition from low to high and high to low. Okay, and this kind of problem we call it the clock feed through problem. Okay, so yeah, the clock feed through I have already explained in the previous one. So this is nothing but if there is a internal capacitances which is in between input and output, so we call it the clock feed through. So this is the problem. So how we can overcome this problem, how we can avoid this problem, and this is really very dangerous state. Like, so we need to reduce what we can do. What is the solution of this problem? The solution of this problem is like we need to design a circuit in a such a way that the internal capacitances should be as small as possible. Okay, so if we are able to design in a such a way, then this clock feed through can be overcome. Okay, so this is all about the different problems associated with the dynamic logic circuits. Okay, one more problem. Yeah, this was the problem which was the part of the signal integrity issues in the dynamic one. So we come up with the 4 different kind of problems. Now let us talk about if I'm cascading 2 dynamic gates, then what kind of problem we can face. So cascading means just connecting two gates back to back. In that case, might be we can face some problem. So what that problem is, let us try to understand. Okay, so suppose I have a dynamic gate, something like this. Okay, this is nothing but this is the inverter based on a dynamic logic circuit, and I have more circuit like this, and the gates of both the dynamic circuit are connected to each other, and output of first dynamic circuit is connected to the input of the second dynamic circuit. Okay, so what we have done, we have just cascaded 2 dynamic gates. This is the one of the dynamic inverter, this is the another dynamic inverter. The clock of both the dynamic inverters are controlled with the same clock pulse, and the output of first dynamic one is connected to the input of the second one. So we have cascaded this one. Now let us try to see what kind of problem this circuit can offer. Okay, so what kind of problem this circuit can offer? Let us see here. Suppose I have a clock something like this. Initially the clock was at 0, so it is charging the dynamic nodes. So this will charge this dynamic node N, because remember, this is really very important. This will charge this node voltage, this will also be charged. So both the node voltage, like output 1 voltage node and output 2 node voltage, will be charged to the maximum, because both the pre-charged transistors are in the on state, because the clock is at logic low. Okay, this is first case. Now let us assume during the pre-charge phase only, if there is some change in the input during the pre-charge phase, if there is some change in the input, it can evaluate only when there is an evaluation phase. But if there is some change in the pre-charge phase, then what will happen? Let us try to observe it. Because let me use the pen. This transistor is in the on state. This is also in the on state. So what will happen? The output voltage, because this is charged, but once the clock is finished, after that period of time, this output voltage will start decreasing. Okay, it will start decreasing, because this is on, and because the clock is at logic 1, so it will be in the evaluation phase. So this transistor and this transistor both will be in the on state, and if both the transistors are in on state, output 1 will start decreasing. Okay, it will start switching the logic from high to low. So this is the perfect case. Now what happens? Because whatever the input is there, like whatever the input we have provided here, it will take some time to reflect at the output. There are some delay between the input and the output. So because this is controlled, because this dynamic logic circuit and the second dynamic logic circuit are controlled with the same clock. So this will also be in the evaluation phase, but it will get the output immediately when I will provide the input. But because of the internal delay, output will be reflected after a certain period of time. Okay, let me repeat it again, what I am saying. Let me clear it, then I will, this is really very important to understand. Suppose the circuit is in the pre-charge mode. So this node will be charged, this node will be charged. Okay, so V out and V out 1 and V out 2 both will be at the logic high. But if there is some change in the input during the pre-charge phase only, so what will happen? There is some change in this one. So what it will wait for to change the clock. So once the clock is changed from low to high, the circuit will go into the circuit will be in the evaluation phase. Now, because input is already it is logic high, and in the evaluation phase, this transistor will become on and this will be on. So this output will start degrading. Okay, but because the input is already in on state and the clock is changed from low to high, this transistor will also comes in the evaluation phase at the same time when the first dynamic circuit comes into the evaluation phase. Okay, but there may be some delay between input and output. Okay, so input cannot change at the output, like input cannot be reflected out at the output at time 0. Okay, it will take some time, but that time delay, until that time delay, the input of this transistor, this input is treating as a logic high. Okay, because it was initially charged, so it will treat as a logic high, and it will this will be in on state and this is always on state. So this voltage will also start decreasing. Okay, and it will decrease up to like the threshold voltage of this one. So it can discharge up to the up to this output voltage reaches up to the threshold voltage. Okay, so if it is less than threshold voltage, then it will be in the off state, and then the output can be there. So so this is what, there is some threshold there is some drop, or there is some output voltage to drop due to the delay between input and the output one. Okay, and this change in the voltage that depends on how much delay we have. So if somehow we are able to manage the less delay between input and the output one, then this change will be reduced. Okay, but yes, there will be some change, there will be some degradation here. So what we have done here, I have the inverter here, I have the second inverter. So I'm assuming that whatever the input I will pass, I need to get the same logic here, because this will be 0 and this will be 1. But instead of logic 1, there is some drop, delta V degradation in the output 2 because of the delay mismatch. Okay, so this is the problem with the cascading one. So how to overcome this problem? To overcome this problem, we can come up with the solution, and then we need to use an inverter between two stages. So if somehow I have used, like suppose I have this kind of structure, and like this is the dynamic inverter, and if I have used one and the second dynamic structure is this one, and if I have used some inverter in between, then this problem can be overcome. Okay, so that because this will match the impedance, because this will not change the logic. Okay, so accordingly, yeah, definitely the output can also be changed. This depends on what kind of structure we have here, but this will solve the problem of the degradation. Okay, so this was the problem with the cascading and the solution with this one. Okay, other than these things, what happens if I am connecting n number of dynamic gates back to back, like I'm cascading n number of dynamic gate back to back, then what will happen? Okay, so see here, and if I'm why we know this domino logic. What is the domino? Domino is nothing but, if we have seen many times like what domino is. So it means that the second line, yeah, this one will be ineffective once the first one will reflected. Like all the stages will not function at the same time, but it depends, like the output of the second one depends on the input of the first one, and the output of second one, third one depends on the input of the second one, and so on. Okay, so this kind of effect, we call it the domino logic, or the domino effect. Okay, the same kind of phenomena can also happen if we are cascading the n number of stages with the dynamic logic circuits. So here we have, let us assume I have a one dynamic logic circuit like this, and if I have another dynamic logic circuit like this, so the output of this second dynamic logic depends on the input of the first one, because there is an inverter we have here. Okay, so if we have an inverter over here, so once this output will be reflected, then it will be passed to the second input, and then it will work. So effectively, suppose I have a 10 number of stages, I have cascaded 10 inverters. So the total time delay will be increased if I have increased the number of stages. So this kind of effects, or this kind of the combination or logic, we call it the domino logic circuits. Okay, so this arrangement we call it the domino logic circuit. Okay.
Hello, sir.
Yes.
Sir, in the previous slide, by adding NOT gate, sir, means we are giving the negative of output to as the
I just told you, the logic will be changed, like, but there it will wait until these, like, suppose input is changing from 0 to 1. Okay, so if it is changing from 0 to 1, so here I will get high to low, and then it will give the low to high again. Okay, so what I am assuming, this output 2 will be the complementary of the previous one. So I told you, like, the output function will not be same like this. So what you need to use, you need to use one more inverter at the output side, so that you can get the output 2. Okay, you got the answer?
Oh yes, sir. Sir, and by adding the NOT gate, the delay will decrease, or?
No, delay will not decrease. Like, because there was see, the clock was connected at the same time for both the logics, both the dynamic logic, and because the input was already in the changing state, it was changing from low to high. So the output will start immediately changing once it will the first logic will go into the evaluation phase. But if I have made in such a way, like, delay of this one, whatever the delay we have is equal to the delay of this one, so we can manage, like, this second logic will not be triggered until this complete logic we will get. So whatever the delay we have here, like, to get the input and output delay, so, like, let us say here, like, this and this, so this is what the delay is, what we can say. Okay, so this will match the delay actually, and at the same time, because see, if, let me repeat it again, suppose if it is 0 and 0, both will be pre-charged, and if the input is changing from low to high, and I have changed this clock to 1, and this clock is also changed to 1, so what will happen, this output will start changing from high to low. But because there is delay between input and output, for some instant of time, this output was logic high, so this will start changing immediately, because we have changed the clock immediately for both the logics, both the dynamic logic circuits. So this is the degradation due to this one. So to make the delay, like, this input or this transistor should not get the input immediately, because we have connected the clock at the same time, we have made some delay, so that it can change the logic, and it should not be reflected, and this drop will be reduced. Okay, you got the thing, or I need to explain it again?
Yes, sir.
Okay, no, still there is doubt. I think from your voice, I'm not convinced actually. If it is doubt, then I will clear it, no problem. So
Sir,
this,
I'm getting that the out one.
yes.
Sir, out one, first it will out one, it is becoming from 1 to 0, but that input and output delay, that I am not getting.
Input and output delay of this circuit?
No, sir, means like in the original circuit, when I'm changing the input from 0 to 1, then I can see that the output is not immediately changing, means the output 1 is not immediately discharging. So then that output will be fed to the second one, and that's why the output 2 will degrade a bit.
See, here what happens here? Oh, sorry. let me connect it all these things, then I will tell you again. See, let me explain it properly. Suppose I have changed the input from low to high. Okay, if I have changed the input from low to high, then what will happen? Let us assume initially the clock was 0, so this dynamic node is pre-charged. Okay, and this dynamic node is also pre-charged. This N1 and N2, these nodes are pre-charged. Okay, now during evaluation phase, if clock is equal to 1 and this clock, so because both the dynamic logics are controlled with the same clock pulse, so this clock is equal to 1, this clock is also 1. So if I have changed the input from 0 to 1, so initially, because this output is at logic 1, because I have pre-charged this dynamic node. Okay, so this is at logic 1, and what cascading means what? The output of the first dynamic node should be treated as an input of the second one, because I have provided some input, and to get the output there will be some delay. Okay, so there is some, might be I have provided the input and I will get the output, let us assume after delta t, because there is always a delay between input and output of any of the circuit. Okay, so if there is some delta t delay, so until that delta t time, because I have made both the dynamic logic circuit in the evaluation phase, so for that period of time, because I have changed the input, so the first dynamic circuit is in the processing state, it is processing the input logic, but because the output one is already high and this circuit is in the evaluation phase, this will treat it as an input, so this circuit will again immediately start processing the things. So what it will do it will consider this output one as a logic 1, so it will start decreasing 0 to 1. So what it will do, it will start decreasing this output 2. Okay, and once this time is finished, delta t is finished, it will maintain the same thing, because now it will get logic 0, and if it is 0, then this will be in the off state, so there is no further discharge of this capacitance, load capacitance, and it will maintain the same logic, and this is what we are getting here. So simply this is based on the how much discharge there is and how much delay it is. So if delta t is very small, delay of this first circuit is very small, then it will take more time to get the previous value to reflect at the second transition, a second dynamic logic circuit. So this is the problem. You got the answer, or still doubt is there?
Oh yes, sir. So now I'm adding the inverter. So sir, the original when out one was high, now it will, while it was processing, while the first circuit was processing.
Yeah, so let us assume, yeah, so let me do it. So low to high, so it will process like high to low, and this will be like low to high. So this was low, so for that period of time this will also be in the low state. Okay, so it will wait for some period of time, so this will not be evaluated until I will not get some input from here. Okay, so either there are two possibilities. Either I can add one inverter here and one inverter here to get the same logic what we expected, or you can add two inverters back to back to make it buffer. Okay, and that will also work. Like it will be delayed by some time, and the effective delay of these two inverters should be same as the delay of this one, so that that will be matched. Okay, so there are many challenges. Yeah, definitely these are not that much simple, like just connecting one inverter you will get you will solve all the problem. But yeah, this is possible, and this is one of the solutions.